Okay, so parabolas often come in standard form, and what standard form simply is it's solved for y. So it's y equals, whatever. They're going to put everything on the other side of y. And there's a couple reasons for that. The main reason is probably that's how it will go in a calculator. So if I were to have a calculator on this and I wanted to graph something, I hit the y equal, it's always solved for y. So most of the time it's just so some technology will be able to deal with it. Well, we're not going to leave it like that. If we have to graph it with technology, we want that. But if we're going to graph it with by hand, which is what we have to do a lot of times, then we are going to put it in the form that we just got done doing. We're going to put it in transitive form so that it's all connected so that we can see the inverses of everything. Okay, so this very first one, that's the parent. That's the one we have to just know. That one starts at 0, 0. And then it goes over 1 and up 1. So over 1 and up 1 from there. And then left 1 and up 1. So left 1 and up 1. So here's the visual, here's the points that go with it. And then over 2, up 2 squared. So over 2, up 4. So over 2, up 4. And then left 2, up 4. Then we could go 3. 3 squared is 9. So over 3, up 9. Over 3, up 8, 9. And left 3 and 9. Left 3 and 9. So there it goes. And then, of course, 4 and 16. And then we could go 5 and 25. And we could go 6 and 36 and so on. But we don't have to do all of those. So there's the parabola. There's the parent parabola. Okay, so we want to turn this one now. This one has some kind of a shift in it. It has something to do with sideways 3. It's either going to go, it's not a multiplier, that it's not going to stretch it high or wide. It's going to shift it because it's it's an addition one. So it's either going to go up it's either up 3 or down 3 or right 3 or left 3. It's one of those 3. Okay, well, let's take a look at it. What we want to do is move things to where they belong. So I'm going to go ahead and pick this. Here's what I mean by moving them to where they belong. Let's compare. We can compare number 2 and number 3 together. See how 3, the parentheses have captured the 3. So the parentheses, you're not allowed just to subtract 3 and put that 3 over there with the y like that. That would not be a legal step because the 3, you would have to square root both sides first. So this one right here has been captured by the x. That's at some kind of an x shift because the x is holding it. If it's not captured by the x, then it belongs to the y. Okay, so we know what this x shift is. Remember, it's the inverse. That means it's going to be a -3 for the x's. And notice the y has no shift on it, so there's 0 shift for the y. So that makes this vertex x at -3, y at 0. So all this 3 did was move it to the left 3. So instead of being at the center, 1, 2, 3 is now where the vertex is. And there's been no shift on the y. And then there are no multipliers, so it's the regular width, over 1, up 1, over 1, up 1, over 2, up 4, 2, 4. And if we want to go another one, it would be 3, 9, and 3, 9. And there we have it. So that one shifted the whole parabola to the left 3. Now, I'm going to start using some graphs on this. So I'm going to actually put that in there. I'm going to say y equals parentheses, oops, not there. Y equals parentheses x plus 3 all squared. Now, notice how this grid goes over 8, up 8, left 8, and down 8. So I'm going to zoom it so my calculator does that also. If I zoom to standard, so I hit the zoom key, and then I'm going to go down to standard. That puts it at 10 to 10 to 10 to 10. So it's very similar to what's happening here. Notice the shift has been over 3. So there's the vertex at 0, 3. If I check the table, if I hit that yellow table right there, I can see the points, 0. So now this is, that point right there is over 0 up 9, which is what that's representing. If I go left 1, so that point right there, as we can see, is -1, 4. So the calculator is going to actually have the specific locations of the points, not relative to here. That -1, 4, I could have gotten 2 because it's over 1, up 1, over 2, up 4, and so on. What I'm going to do with the calculator here is also compare it to x squared. So I'm just going to put on y2 x squared and now graph both of them. So see, that's where the apparent was, and then it got slid 3 to the left, and that's what that 3 did. Okay, let's look at this one. See how this 3 has not been captured to the x? That square right there, the parabola part, is only on the x, so I could actually put parentheses there. Now this 3 can be moved. So that 3 doesn't really belong to the x, it belongs to the y. If I move that 3 over here, I'll move it to the other side, we'll make it -3. This problem in transitive form is really y minus 3 equals x squared. See, here's the shift for the y's now. The y's are a positive 3 shift, and the x's, there's no shift on that one. Okay, so that means the vertex here is at 0, 3. So 0, 1, 2, 3. So that 3, when it was like this, was an up and down shift because it really belonged to the y's. And the y variable is the up and down variable, and the x is the sideways variable. Okay, and then there's no multiplier, so over 1, up 1, over 1, up 1. It has a normal kind of width and height, so over 2, up 1, 2, 3, 4, over 2, 1, 2, 3, 4, and there's that one. So that 3 shifted it up 3. Now if I take a look at that in my calculator, I'll just change this. Let me get rid of that. I don't even need the parentheses, they weren't there originally. And then there was a +3. So the calculator will now, there's the shifted up 1, and there was the normal 1. So it's the normal width just shifted up 3. Okay, so take a look at number 4. See, that 4 has been, I like these problems because they both say -4, but they both don't really mean -4. So that 4 has been connected to the x. This 4 really belongs over there with the y. So if I rewrite that in the form that's easy to graph in our head, that -4 comes over here as +4. Okay, here's the x inverse, so the x shift is going to be +4. And here's the y inverse. Now what makes that add up to 0 is a -4, so the y is a -4. So even though it started out as a -4 and a -4, one of them was positive and one of them was negative. So the vertex, the x part is 4 and the y part is -4. So 1, 2, 3, 4, 1, 2, 3, 4. So the vertex now is down there. So the multiplier on the x is just a implied 1, and the multiplier in front of the y is an implied 1. So there's no multiplier stretches other than normal. So over 1, up 1, over 1, up 1, over 2, up 4, over 2, up 4, over 3, up 9, over 3, up 9. And now if I needed to, I could identify any of these points on there because I just graphed it, like that point right there. All I have to do is look. From 0, 0, that's over 1, up 5. So 1, 5 is one of those pixels on there. So if I were to graph that on my calculator, so I'll type it in exactly how it was. Y equals x minus 4 all squared minus 4. That should start down here at this vertex. This dot right here is at 4, -4. That should be where it starts. And then it has normal height. So the dot 1, 5 should be on the table. So if I take a look at the table right here, second table, sure enough, right there's 1, 5. That's this dot. Look at this one right there. That's over 2, up 0. Okay, that's right there, over 2 up 0, and so on. 4, -4 should be on there, right there. There's 4, -4 was the vertex. Okay, let's take a look at number 5. Now there is a multiplier. But now remember, the same thing is happening here. Okay, that multiplier is on the outside. There's not one real close by. I should have made one just a little bit different. Okay, I just want to compare these two. Whether the 3 belongs to the x or doesn't belong to the x. See, here the 3 belongs to the x. So the inverse of that would be 1/3 on the x's. So the x's would be 1/3 as much. All of the x values would be multiplied by 1/3. Here, it would be okay. I can, just like over on these, if it's not connected to the x, you can move it to the variable that it belongs to. Well, that's what I want to do. It's not been connected to the x. That 3 has not been captured by the parabola part, by the square. So I'm going to divide both sides by 3. Now, dividing by 3 is the same as multiplying by 1/3. So I'm going to multiply both sides by 1/3. So really, this is 1/3 y equals x squared. Now I have a multiplier. Multipliers are the inverses are trying to force 1. So what this means is all of the y's are going to be tripled. Okay, there's been no addition shift, so it's going to start at 0, 0. But all the y's are going to get tripled. Okay, so we know that the next parent shape should have been at 1, 1. But the y's are getting tripled, so it's at 1, and that 1 gets tripled. So over 1 up 3, so the ups are getting tripled. Over 1 up 3, because that would have been the next point, -1, 1, but the y values are getting tripled, so -1, 3. That's that dot. Okay, I know it's supposed to, if it was a normal kind of a width or height, it would be over 2 up 4. It would be right there. So I'll make the red one what the parent would have been. So 1, 1, and then 2, 4. But the y part of that is getting tripled. So instead of going over 2 up 4, this 4 right here is getting tripled. So it's got to be over 2 up 12. So over 2 up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then this one over 2 up 12. Now there's certainly times where I'll ask you, okay, specifically, what is that pixel right there? Okay, well it was over 2, so that pixel's at -2, and then it went up 12, so that pixel right there is at -2, 12. That one right there is at 1, 1, 2, 3. And see, I can actually tell it should have been here, but it ended up at 1, 3. The -2, 4, that's what it should have been, but the y values got tripled, so it ended up at -2, 12. So that 3 right there didn't do anything to the x. It really did something to the y. It made the y's 3 times taller. Okay, well, what about this one for number 6? Again, the 1/3 has not been captured by the x, so I can multiply both sides by 3. So really this was 3y equals x squared. The inverse of times 3 is times 1/3, so all of the y's now are getting multiplied by 1/3. Okay, so whatever the vertex is, the y's are going to get multiplied by 1/3, so 0, 0, fine. The next one should have been 1, 1, but the y is getting 1/3, so it becomes 1, 1/3. Okay, so over 1 up 1/3. And then -1, 1 becomes -1, and the y's get 1/3, so -1 up 1/3. See, it's making it 1/3 as tall. Okay, the next parent pixel was at 2, 4. but we're going to multiply the y part by a third. So it'll be 2 4/3. So over 2 up 4/3. 4/3 is 1 1/3. So over 2 up 1 1/3. Over 2 up 1 1/3. I'm going to do the 3 9. Okay, the y part gets thirded. So 9 times a third is 3. So over 3 up 3 is another exact pixel. And over 3 up 3 is, over 1 2 3 1 2. It should be right there. 1 2 3 1 2 3 right there. So here comes, there goes the new one. Now we could actually get one more because 4 16, and the 16 gets thirded, so it'll be 4 and 16 thirds, so that's 5 and a third. 1 2 3 4 1 2 3 4 5 and a third. See, it's right where it's supposed to be. That thing is going on up for 1 2 3 4 5 and a third. It'll be right there. Okay. Now look at number 7. See, the parentheses have captured. That parentheses is supposed to be right there. Fix that one. The square is capturing the 1/3. Okay, there's 2 ways that I want to show you how to do this, and both of them are fine. We can just think of it right here. The 1/3 has been captured to the x. Okay, that means its inverse is times 3, so all the x's are going to get times 3. This is going to make it 3 times wider. Okay, so my 0, 0. Now the x's are times 3, so these numbers going down this way are times 3. Well, 0 times 3 is still 0, so that doesn't do anything to that one. But the next one it will, 1, 1. The x's are multiplied by 3, so 1 times 3, that puts that one at 3, 1. And the next parent is negative 1, 1. See why we have to know the parent points? So now the x is getting multiplied by 3, so that's going to become negative 3, 1. I can start plotting these. I can plot them as we go. 0, 0, 1, 2, 3, 1, 1, 2, 3, 1. See, that 1/3, its inverse is times 3. The x's are 3 times wider. It's making it go 3 times as fat. The next parent was 2, 4. But now the x gets tripled, so it makes it 6, 4. And then the next parent was negative 2, 4, so tripling that is negative 6, 4. So 6, 1, 2, 3, 4, and negative 6, 1, 2, 3, 4. The next parent would have been 3, 9. But we're tripling the x, so it becomes 9, 9. 8, 9, 8, 9. It's right there. So the other one is 9, 9 right there. And there is this. So this one, there's the new parabola stretched 3 times as wide. Okay, let's hold off on, I was going to say something else, but I'm going to wait on that just a minute. Okay, it looks like all of these got mistyped. That's supposed to be right there. The square, I wanted the square to catch that 3. Okay, see how the 3 is captured to the x? Now this time all of the x's are going to be 1/3 as much, because 1/3 is the inverse of 3. So 0, 0. Now all of the x's are going to be multiplied by 1/3. Okay, 0 times 1/3 doesn't do anything, so 0, 0 still. Okay, but then 1, 1. Okay, this 1 is multiplied by 1/3, so it's going to become 1/3, 1. And negative 1, 1 is going to become negative 1/3, 1. Okay, so 0, 0. And thinking about what this should look like, it's going to be 1/3 as wide as the parent. Okay, so skinny. This one is going to be in skinny. 1/3, 1. So over 1/3 up 1, over 1/3 up 1, right there. Let's do the 2, 4. Okay, the x gets thirded, so that's going to make it 2/3, 4. So if I go over 2/3, 1, 2, 3, 4. If I go negative 2/3, 1, 2, 3, 4. What about the next one? 3, 9. But the x value gets thirded, so 3 times a third is 1. So 1, 9. Over 1 up 9. Over 1 up 9. And there's that parabola. It looks like it got really skinny. In fact, it got 1/3 as wide. That's what that inverse was saying. Okay, I'm going to go ahead and show you another method now on that one. So here would be an alternative way to do it. I'll do it in a different color. We started out as y equals 3x all squared. We could go ahead and multiply that out. There's no addition there. So since there's no addition there, the square just goes on everybody. So that would be the same thing as 9x squared. And now I can move the 1/9. See, now the 9 is not connected to the x when you do it like that. So if I 1/9 both sides, those are gone. So we have 1/9 y equals x squared. And now look, this is saying that the y's can be multiplied times 9. The inverse of 1/9 would be times 9. So if I did it that way, 0, 0, now all the y's get multiplied by 9, so that's still 0, 0. That's the same dot as I had. Now 1, 1. Okay, the y's are getting multiplied by 9, so it'll be 1, 9. Notice that that was a point over here also. 3, 9 became 1, 9. Well, now the 1, 1 becomes 1, 1, 1, 9. Over 1 up 9 is right there. And if we do the negative 1, so negative 1, 9. So see, these 3 red dots are in the exact same location as the 5 black dots were. So you can actually do that either way. You can multiply it out or not multiply it out. Okay, let's take a look at when there's 2 of them. Okay, and again, that square is supposed to be out there. I wanted the square to capture all of that. Okay, this 2 belongs to the y, that 2 stays with the x. So if I multiply both sides by 1/2 to get rid of that 2, the problem is really 1/2 y equals 2x squared. Okay, the inverse to this one is times 2, so all of the y values are times 2. The inverse to this one, all of the x values are times 1/2. So this is going to be 2 times taller and 1/2 is wide. So if I start to take a look at what these should be, the x's are getting halved and the y's are getting doubled. Well, half of 0 is still 0. Twice 0 is still 0. So 0, 0 is still the vertex. You good? Okay, the next parent point is supposed to be 1, 1. But the x value is getting halved and the y value is getting doubled. Okay, so over 1/2 up 2. The next parent shape is negative 1, 1. So the x value is getting halved and the y value is getting doubled. So that one's becoming negative 1/2, 2. The next parent shape was 2, 4. Okay, the x is getting halved, making it 1, while the y is getting doubled, making it 8. So over 1 up 8 is the next specific location. And then negative 2, 4 will become negative 1, 8. And there's 5 exact pixels of that parabola. Okay, so the x it's half as wide and twice as tall. Okay, this negative right here, notice how it has again, that should be like this. It's not been captured by the square, so this negative, I can multiply both sides by a negative. It really belongs to the y. So that negative right there affects the y. So that's like an implied -1. Okay, I need to remember, multiplicative inverses try to force +1. So I need another -1 for all of those. So in effect, it's going to turn it upside down. All of the y's just get negated. So the 0, 0 becomes 0, 0 still, but the 1, 1, the y becomes negated. So that's going to become 1, -1. So 0, 0, over 1, down 1, over 1, down 1. The 2, 4, the y part gets negated. So 2, 1, 2, 3, 4, 1, 2, 3, 4, and then 3, 9. Instead of going over 3, up 9, it will go over 3, down 9, and over 3, down 9. So it looked like that negative was on the x in the first place, but it was not because of where the square was. Okay, this one I wanted the square. All of the brackets, I'm going to reprint this paper for you guys so that they're in the right spot, so I'll just keep fixing on mine. So that little square should be on the outside of the bracket. Okay, first of all, I just want us to think about this. Here's our brain. I want to put this in a thinking bubble. We have y equals negative x all squared. Well, if I square this out, a negative times a negative is a positive, and an x squared. If I actually do the squaring, the negative ends up going away. So that actually should look like exactly, if we multiply all of this out, it's the parent function. It's just over 1 up 1, over 1 up 1, over 2, 4, and 3, 9. That's just the parent function. Well, how can that make any sense? Well, it's a -1, right? Okay, that means the inverse over here for the x's all get multiplied by -1. Well, let's take a look at that. Does that do anything? So all of the x's are multiplied by -1. So all of these numbers are multiplied, all of these numbers are multiplied by -1. Okay, so 0, 0. But 1, 1. Okay, that's going to make this a -1, 1. So it is actually changing it. I was supposed to, so 0, 0 is fine. I was supposed to go over 1, up 1, but now I'm going left 1, up 1. So left 1, up 1 is right there. But what about the other point? -1, 1. When I negate that one, it turns it into 1, 1. So now it's over 1, up 1. See what happened? The left side went to the right and the right side went to the left. It switched that parabola this way, sideways. But the parabola is symmetric. This tail went over there, but that tail went over there, and it ended up landing on itself. So it actually did go back to what it was. It flipped itself left to right, but it landed back on itself. So over 1, up 1, over 1, up 1. So the next one will be 2, 4, and 2, 4, and then 3, 9, and 3, 9. So that's a unique property for parabolas, is if the x part is negated, it actually doesn't do anything because squaring a negative makes it go away anyway. Okay, there's a little trick when you put it in transitive form that we have to be aware of. The x must be clean. It doesn't matter what that number is, that's why I put, it doesn't matter what that number is. It's this number, that must have an invisible 1 in front of it. You cannot have a number there like this 2. So what I'm saying is, this is a problem. That 2 is a problem. Sorry, that 2 is a problem. It can't be like that. We have to factor that 2 out. What happens is that 2 is making that shift not really a 6. It's not really shifted a 6. All of this stuff has been captured inside the square, so it all belongs to the x. The x is going to be half as wide, and it looks like it's going to be shifted +6, but it's not. We have to rewrite that so that the x term inside there is clean, has no numbers on it other than 1. Okay, here's how I'm going to do that. Well, it does still all have to stay part of the x. So I'm going to make it all still squared. But inside that, I'm going to factor out the 2. I'm going to divide out the 2 and see what's left. If I divide a 2 out of that, there's an x left. And if I divide a 2 out of that, there's a 3 left. That's really what it is. This is a shift of 3. That means it's going to go to the right 3. So the x's are getting added 3. And then the x's are also half as much. Okay, so we should be able to deal with that. So first of all, the vertex is going to get shifted over 3. So the new vertex, it's going to be 3 for the x, and there was no shifting on the y. So the new vertex is at 3, 0. Okay, I'm supposed to go over 1, up 1, over 1, up 1. Okay, but that's not what I'm going to do. The x's are half as much. So I'm going to pretend like that is 0, 0, even though it's been shifted. I'm supposed to go over 1, up 1. But the x's have been halved. So I'm only going to go over a half, up 1. So instead of going over 1, up 1, I'm going over a half, up 1. And then left a half, up 1. Then the next one, I'm supposed to go 2, 4. But the x's are getting halved. So half of 2 is 1, 4. So from the center, I'm going over 1, up 4. And over 1, up 4. Whereas in the red, I was going to go over 2, up 4. So see, the red one would have been there. The red one is going to end up being pretty wide. That's the parent. The one we want is the black one. It's half as wide. 3, 9 would have been the next one. Okay, well, I'm halving the x's, so it's 1.5, 9. So over 1.5, up 9. Over 1.5, up 9. So here's 5 exact pixels of this problem that was half as wide because of the 2, and then it was shifted right 3 because we've got to factor that 2 out to really see the true shift. Okay, that's an issue sometimes. So let's take a look at number 13. Okay, there's no multipliers on this one. This one will be a real quick and easy one. Put the 2 over there. So y minus 2 equals x minus 1 all squared. That means the y's are plus 2 and the x's are plus 1. So the vertex is at 1, 2. So over 1, up 2. There's no multipliers. That multiplier is a 1. That multiplier is a 1. So it's the normal width and height. So over 1, up 1, over 1, up 1, over 2, up 4, over 2, up 4. The next one would be 3, 9, but I've got 5 points here. That's enough. We have it graphed. 14 has a multiplier, so we've got some issues on this one, so we've got to deal with that. So first of all, I'm going to move the 3 to the other side.